So we will now be discussing kinematics of a moving point. Okay, so let's just put that down. So, okay, there you go. Kinematics. So if you have a material, okay, and there's one point, material point of reference. This is the material point of interest. Okay, so whatever we are talking about right now, it is about that one particular point in the material. Okay, it's not for the whole rigid body or the whole material in itself. So let's define when do we actually say it's moving, okay, and when it's at rest. So a point is said to be at rest relative to reference frame F if it continues to occupy the same location of F otherwise it is said to be in motion. Okay, so a point is said to be at rest relative to a reference frame F if it continues to occupy the same location of F, otherwise it is said to be in motion. Okay, so we'll put out this mathematically now, okay, in terms of what we have learned before. Okay, so we have learned about a position vector before, so we'll be using that and see how this can be defined. Okay, so let's put out a say a frame like this, and then you have a path like this. Okay, so then we have P1 and this is the trajectory. So this material point is moving along this trajectory, okay, and its position is P1 at time t1, is P2 at time t2, and P at any given time t. Okay, so clearly this is RP1 based on what we have learned about position vectors before, that if it's with respect to O, we drop the other subscript. Ideally we should have written it as RP10, but since it with respect to O, we drop this term. Similarly, this particular term will be, this vector will be RP2, and this will be equal to Rp of t, okay, at this given time. Now we can also draw one more say O dash, okay, some other reference point, and for that and then this, sorry, this is RD vector, okay, this is the displacement vector with respect to the frame F. So I hope the colors are self-explanatory. Okay, so you have the position vector of a moving point P in a frame F. Okay, this is a frame F over here, and its location is occupied by it at time t relative to a reference location O of F, and is denoted by Rp of t over here. The function Rp of t is defined as a continuous function of time. Okay, so we have to write this because it's important. Rp of t is defined as a continuous function of time. Now here is a riddle which you should try to answer. Why is this needed? Why is this definition? And by this we mean this continuity. Okay, so the answer will follow indirectly, but you should look out for this. So we are defining Rp of t as a continuous function of time, and let this moving point P, as I have already said, occupy the locations P1, P2 of the reference frame F at times t1 and t2 respectively. Okay, then the displacement vector with respect to frame F from t1 to t2. Okay, so as an observer you are observing two events. Okay, one is that the material point of interest is at P1 at time T1, then some interval has passed and you are now at time T2, and this material point is now at P2. So the displacement is in the frame F is P1, P2. This is actually a definition. Okay, remember there were axioms, and remember that there were defined entities. So I am defining this displacement over here. Okay, so it's the directed line segment P1 to P2, which is shown in green color in this diagram. Okay, this is equal to R of P2, sorry, R of P2 P1, which is equal to Rp2 minus Rp1. Okay, so this is 1.6. One of the other definitions which you should know is that the motion of the material point, okay, since we are discussing the movement of a material point, the motion of a material point is said to be spatial if it's in 3 dimensions or it is planar if it's in 2 dimensions. So when we have defined the displacement as this vector p1 p2, we refer to a general one. It's not planar or spatial as such. It can be anything. And if it's clearly in a straight line, then it is called rectilinear. So okay, if it's along a straight line. So if it is planar, it can be either curvilinear, sorry, it can also be called as curvilinear, basically when it's not in along a straight line. So it can either be spatial or it can be planar, but not along a straight line. So if you have, so one example of spatial curvilinear is a nut being titled on a bolt. Okay, so you should be able to look at a video of it. So you can go to any search engine which you use and look for a video of a nut being uh, tightened on a bolt. Okay, just for your information, this is actually a non-permanent joint. Okay, so in the larger category it comes under screw. You know what a screw is, nuts and bolts, and you must see in the things around you. Okay, so try to find. On the other hand, there may be some permanent joints. Okay, say an adhesive like a Fevikwik which we use, or a rivet, or a weld. Okay, so there are two kind of joints, permanent and non-permanent, and you should observe at least the motion of a nut being tightened on a bolt. Okay, and why is it a spatial curvilinear and not rectilinear? Okay, okay, now let's try to define some of the other terms, okay, like the velocity and acceleration. So let's now come back to another diagram. So you have the again we have a trajectory of the motion of a material point. Remember, we are not assuming that the whole body uh, is assumed to be a point. Okay, we are not doing that. We are referring to a whole material itself, and then our interest is only in this one point. Can be another point, can be a third point, but any one specific point. Okay, the whole rigid body is not being assumed into one point. Okay, so that's the trajectory, and let's draw a few of these. So let's draw it with respect to O. Let's say we have this point P over here, and that's S. S is the uh, trajectory. Okay, and it has now moved to this point. Clearly this is O, so this is Rp of t. Okay, and this is Rp of t plus delta t. Okay, so this point has now moved to this place P dash of S plus delta S. And clearly you have a displacement now, which is, I'll show it with what sign. Here I had shown it with green, so let me just continue that with green. This is the displacement, that will be delta Rp. Okay, so we have now a moving point P, which occupies the locations P and P dash of frame F at times t and t plus delta t. Okay, so at time t it occupies P, and t plus delta t it occupies position P dash. Okay, so then the displacement, according to the definition which we have just used or defined, is delta Rp, that is equal to P dash. Okay, now we want to define now the velocity. Okay, so the velocity of the point P in the frame F at the time t is equal to the limit of delta t tending to 0 P dash as delta t. Okay, this is limit of delta t tends to 0 delta Rp delta t is equal to Rp of F. This is again defined like this. Okay, a dot in this course automatically means a derivative with respect to time. Okay, so that will be continuing throughout. This is equation 1.7. Okay, now similarly the acceleration is defined in the frame F at the time t is equal to, okay, at the time t, and this is equal to R double dot P of F at time t. This is again defined. Okay, so this is the displacement, velocity and acceleration of a material point have been defined over here. Okay, okay, so now let's see some other geometry related to these definitions. So as delta, oh sorry, I should use a black ink. As delta t tends to 0, the chord delta rp in green, okay, delta rp in green, perhaps I should make it slightly more clear. That's the risk, okay. And this delta rp, okay. Okay, so the chord delta as delta t tends to 0, delta the chord, the direction of the chord, let me put the direction, the direction of the chord delta rp is along the tangent. You can do this yourself, okay, make this delta t so small and you will observe that this direction of delta rp will actually be along the tangent. So let me do that over here in another ink. So this is actually drp by dt. Okay. Okay, so the direction of the chord delta rp is along the tangent, and hence this so-called dr by rp by dt is equal to delta, so the limit of delta t tending to 0 is delta rp, okay, by delta t. So once this is clear, we can say that the velocity vector is always tangent to the trajectory, because the velocity vector is equal to this limit of delta t tending to 0, delta rp by delta t, or rp with respect to f dot. Okay, so this is the same as rp. Okay, and this is the velocity. So that's always tangent to the trajectory. Now, since the velocity and acceleration are dependent on this vector p1, okay, sorry, pp dash, okay. Now we want to see that how much will the definition of velocity and acceleration actually change if you don't really take the point reference as O, but something like O dash, okay. So let's do that. Let's take another point O dash, and now this will be R P dash T, and then this particular thing will be, I'll just write it, rp dash t plus delta t. Okay, so we have now defined it in terms of O dash. But here is the thing. It is only concerned about the vector pp dash, which is independent of whether you take the point O or O dash. We have already seen that before. Okay, so this implies that the displacement the velocity, let's say the velocity okay, actually we can say the displacement of the point P. I don't know why we are not saying that. Okay, the velocity and the acceleration a p of f of p depends on f but are independent of the choice of the origin and orientation of axis x, y, z. This last part you can easily verify from this derivation which we have done, that it does not actually depend on the orientation of x, y, z, your coordinate axis. Okay, embedded in the frame F. Frame F. Okay, so I hope this concept should be clear. Okay, now we want to now go back to this situation where we define the rest and motion again. So clearly, I mean, P, this material point of interest in a big rigid body, is at rest in frame F. See, you should never ignore the frame. You have to mention the frame. Okay, it's not an option, it's a necessity. Since all these definitions of displacement, velocity and acceleration are with respect to a particular frame. Okay, so P is at rest in frame F if the position vector of this P is equal to the same as it was at time equal to 0 for all time. Okay, so wherever it was at t equal to 0, it continues to remain at any given t. Okay, so P is fixed in F if, this means if and only if. Okay, velocity of P with respect to F is equal to 0 for all t. Okay, now there is another definition. We say that P is at instantaneous rest in F at t1 if vp of f t1 is equal to 0 and the acceleration of that point, okay, at any at this at the same time is not equal to 0. Okay, so that's the difference between being and rest and being at instantaneous rest. Being and rest means it is now velocity is 0 and the velocity will continue to be 0. That will only happen when the acceleration is 0. But being at instantaneous rest means the velocity right now is 0 but the acceleration may not be 0. In that case there is a possibility that the velocity will be anything different from 0. So that's instantaneous rest. Okay. So as we move ahead in this course, we will have lots of subscripts in the notations. So we shall drop the suffix p and the frame of reference from now on. Okay, but you should not drop it at least when you try to learn the subject from the start. Okay, gradually when you become comfortable, you can drop it. So we shall drop the suffix subscript p and even this frame, okay, when they are clear from the context. So the velocity is written as time derivative of the position vector. The acceleration is written as the time derivative of velocity, which is double time derivative of the position vector. So this is equation 1.8. Okay. Now since it's a vector, both the velocity and acceleration, what would be the direction? So the direction of this would be the vector v divided by its modulus, and the direction of the acceleration would be this. Okay, so we know this. I mean, this would give us a unit vector. In general, the magnitude of the vector A is not equal to d by dt of the magnitude of the vector v. Okay, this is something which you should remember. We write v is equal to, sorry, A is equal to dv by dt, not the magnitude of A is equal to d by dt of the magnitude of v. So this is something which one should remember. Now let's try to integrate it. Okay, integrate this equation 1.8 and try to arrive at the velocity. So the velocity of, so which we can say that integrate equation 1.8 plus 0 to t acceleration of t dt. Okay, so basically you are integrating this particular part. Okay, and you have already added a constant of integration. Okay, that's the initial, so-called initial velocity. If you were indefinitely integrating it, you would get a constant of indefinite integration, but right now you have this. Okay, and similarly, if you now integrate this particular part, okay, sorry, this particular part, we will get r of t is equal to r of 0 plus 0 to t v, okay, and this is equation 1.9. So let me just now remove this. So these are the two equations which we get after integrating 1.8. From this, okay, we can further derive that v square of t minus v square of 0. So when we say 0, it means t equal to 0, okay, and this is definitely between v square of 0 and v square of t. This is dv square okay, and then you have 0 to time. Now this can be written as t by dt. We have changed the variables of integration, and that can be set by t by dt v dot dt. Okay, I hope you know how to write this. Okay, okay, this is not a multiplication and division by dt. Okay, you should know what are the arguments which make this possible. Now this again can be written as you can, what you can do is you can apply the chain rule of differentiation. So you will have a v dot v plus v dot v dt, okay, and this is equal to 2 times of 0 to 2 and v dot v dt equal to 2 times of r0 r of t a dot dr. Okay, the reason is that let's see the reasons. This can be written as this because a dot b plus b, sorry, a dot b is equal to p dot a. Okay, what is this property called? Okay, there is a name for this property, associative, commutative, distributive, whatever it is. Okay, you should be able to find that out if you are not able to recall. And secondly, this has happened because this particular thing can be written as dr, okay, and v dot can be written as the acceleration. Obviously the variables of integration have to be changed from time to position. So that's how these two things can be done. Okay, now if you have a, if there is a uniform acceleration, means the acceleration is not changing with time. So acceleration at any given time will be equal to a naught. Okay, so a naught is a constant vector. Remember, every time we say there is a constant vector, it just does not mean that the magnitude is constant. It also means that the direction is constant. So a naught is a constant vector, meaning both its magnitude and direction are constant in time. Okay, so in this case, equation 1.9 becomes, so there are three equations in 1.9. They will become velocity of t is equal to velocity of u plus similarly you have the position at t is equal to r of 0 plus v naught of 0 t, okay, plus half a naught t square. How would this come in? You have to substitute this definition of velocity over here, okay, then you will be able to get this. And please do that, okay, don't like leave or skip ahead thinking it's too easy. And finally the last one can be written as v square by t, v square of t minus v square of 0 equal to 2a naught dot r of t plus r of 0. So this is equation 1.10. Okay, so this is what we get if you have the acceleration as a constant vector, meaning it's both constant in magnitude and direction. Okay. Now if one choosing r of 0 is equal to 0, what would this mean? It means that the position vector of this material point of the material body, okay, is actually at the origin. Okay. If this is done in expression for r of t, okay, this one, then this will show that trajectory is a plane curve in the plane v of 0 okay and a of 0. Okay, now what do we mean by saying that the vector r is a trajectory in a plane curve in a is a plane curve in the plane v and a naught? Okay, so this is what we mean, that this vector r of t will be written as v of t plus half of a naught t square. I can also write it as t of v naught 0 plus t square by 2 a naught. Okay, now remember, you could say that, say you have this vector 2i plus 3j, okay, you could say that this is a vector, I'm not using r, let me call it, I don't know, q. So q is a vector in I and j plane, okay. Similarly, r is a vector in v and a naught plane, okay, in the plane of v and a naught, just like this vector q is lying in the plane of I and j. So that's all. Okay, it is being written in terms of these two vectors. So that's the meaning of this, that the RT is a trajectory. Trajectory is a plane curve in the plane of v of 0 and a0. Now, if you have for uniform motion, there is no acceleration. Okay, this is uniform motion. A0 is equal to 0. Okay, then equation 110 will give, remember it was anyways a uniform acceleration. Now even in that uniform acceleration we are saying that the acceleration is actually 0. So there was never actually acceleration, there will be no acceleration either in magnitude or in direction. So that will give us velocity of t is equal to this value, meaning the velocity will remain unchanged. The position will be equal to r0 plus v t. So the position vector does change. So this is a straight path. Okay. So this is something which you should verify easily why it's a straight path. Look at the plane in which it is the trajectory is drawn. Okay, so you have to use this idea. You have to look at the plane, what are the trajectory is moving in which plane. Okay, that should give you an answer to this. Okay, so the next what we would want to do is to define the V and A in an extrinsic coordinate system. Okay, so the one is Cartesian, the more famous x, y, z. The other is cylindrical, which is r, phi, and z. Okay, and then also we have the so-called intrinsic coordinate system, when we have to also define V and A in intrinsic coordinate system. This is essentially the called path coordinates. Okay, so you will see both of its values. Okay, and in these cases, I mean, there's also a spherical coordinate system, or there can be some other coordinate system, but these are the two which we'll be focusing on. Okay, so the coordinates are given a priori, it is fixed, and in this other case the coordinates are not given a priori. Okay, so they are moving. So both of them have their value in mechanics based on the situation, hence we'll be learning both of them. So let's start with the kinematics of a point in Cartesian coordinates. So we write kinematics of a point in Cartesian coordinates. Okay. So let x, y, and z be the Cartesian coordinates. So let me just draw a nice diagram, or at least as nice as I can draw. Okay, so let me draw. So the coordinate axes are fixed, okay, in extrinsic one. So you have a y. This is the frame F. Okay, you have y, you have x, and you have z. Okay, and you're observing this point P, the motion of this point P, which clearly can be written as rp, okay, as a function of time. So you know the unit vectors I, j, k will lie along the x, y and z directions, okay. So I'm not separately writing them. Okay, so based on this diagram, the position vector, or which is r, this is r, is equal to x coordinate with respect to time, okay. So at the given time, so let me just see if I can draw it. So this is x of t, okay. Then we move like this. This will be y of t, and then we move up along the z direction. This is z of t. Okay, so I hope these visualizations are clear. So if you have to write the position vector of this material point, that would be I plus z of t. Similarly, the velocity. Remember what was the velocity? It was the time derivative. It was the time derivative of the position vector, okay. And similarly, the acceleration was the 2-time derivative of the position vector. So we'll be just writing that over there. So the velocity is equal to x dot I plus y dot j plus z dot k. So I have skipped the argument of time in x, y and z, but it is implicit, okay, because your dot means a time derivative, so it has to depend on time. Similarly, the acceleration of this is equal to x double dot okay. So this is how we can write the position and the velocity and acceleration. So v is a vector which has 3 components along the x, y and z directions. So the velocity, the component of the vector v along the x direction is x dot. Similarly, the component of the velocity along the y direction is y dot. The component of the velocity v along the z direction is z dot. Similarly, the acceleration ax is equal to x double dot. It is also equal to vx dot. Acceleration of y along the y direction is y double dot. It is also equal to vy single dot. Sorry. Okay, so this will be vy dot, and az is equal to and the magnitude of the velocity vector at any given time will be given by vx square plus vy square plus vz square, that's x dot square plus y dot square plus z dot square. Similarly, the magnitude of acceleration is ax square plus ay square plus az square. So this is x double dot whole square plus y double dot whole square plus z double dot whole square. Okay, so this is equation 1.12. Okay, so this is all in Cartesian system, hence this is becoming very comfortable to understand and visualize. So that's a good thing. Okay, in general, ax is equal to x double dot, ax equal to x double dot may be a function of x, y, z, meaning the position at which the material point exists, and the x dot, y dot, and z dot along with time. So this is the most general form. Okay, because the acceleration is actually depending on the position and the velocities. Okay, so in most general form. So you should be able to convince yourself of this. Okay, you can pause the video and think about it and convince yourself and then move ahead. Okay, that in general ax equal to x double dot may be a function of x, y, z, x dot, y dot, z dot, and time. So you will have three coupled differential equations have to be solved. Okay, so this implies that three coupled. Coupling means that they are linked to each other, they are not independent. And you should already be knowing what a differential equation is. To get x of t, y of t, and z of t if a is given. If a, okay, so we already had some idea of how this will be going along. Okay, I mean we had done an integration above over here, so this was the differential form already over here. Okay, then we converted into this, we integrated this. Okay, so there is similar sort of a sentiment contained in this argument. Let's take an example. If ax is equal to x double dot is a function f1 of x, x dot, and t. Okay, then it can be integrated just like in rectilinear motion. So we have already done that in the previous section. Please check and see whether you will be able to do this or not. Okay, this is a good time to put that knowledge to test. See if you can do this. Okay, just go to the previous section and check if you can do this. Okay, so if this material point, okay, one point in this large rigid body which we have has a planar motion, meaning it's in so-called 2D. Okay, then perhaps you can skip the z coordinate or skip the coordinate in which the movement is not there. Okay, you can align the system like that. Okay, so let's see. So if the point has a planar motion, then a good choice of the coordinate system is xy plane is the plane of motion. So in conventional solids mechanics, at least we use xy if there is only a 2D situation, because z is normally associated with thickness. So a similar sentiment is going on over here, that if it's a planar motion, just stick to the xy system and get rid of the zy. And if it's a rectilinear motion, okay, then you will just say that motion is in x direction. It's a convention, okay, not binding on you. Though you will realize that not following this convention doesn't really constrain your thinking in any way, okay. So you are free to take a rectilinear motion in the y and z direction as well, no problem at all. Okay, so one can have implicit, sorry, implicit definition of trajectory. So you can say that g x comma y comma z is equal to 0, or h x comma y comma z is equal to 0. Okay, let's call it. The part important over here is that time t is not explicitly contained. So that's why it's the implicit definition of a trajectory. Okay. So what would be the trajectory be? Well, it will just be the intersection of these two, g is equal to 0 and h is equal to 0. Okay. The curve of intersection of two surfaces described by equation 1. Equation 1 is over here. Okay. So you can try to do this. I mean, if two surfaces are, say, a plane and a spherical surface, what would be the trajectory be? Okay, or you can invent your own exercises. I mean, if you have a conic section like a with a plane, then what would be the intersection between these two? Okay, so what would be the path, what would be the trajectory then? So that's the idea contained over here. Okay, so if one wants to calculate the acceleration and velocity, okay, we can do it with respect to time for over here. So let me just take a simple example. Let's say that the plane trajectory, okay, is f of x comma y is equal to 0. Okay, say this is a circle, for example. You know what will be the trajectory, what will be the two surfaces when the trajectory comes out to be a circle, for example. Again, we are not working with that, but just as an example. So if you the plane trajectory is this function fx comma y is equal to 0, you can differentiate this with respect to time. So that would be dou f by dou x into x dot plus dou f by dou y dot is equal to 0. So this shows the partial differentiation, okay, because f depends on x and y both. So this is a partial differentiation with respect to x, this is a partial differentiation with respect to y, and clearly x and y have time into them. Okay, that's implicit, that's why we are not explicitly writing. So that's why you have this x dot and y dot. Okay, now this should give us the velocities, and for acceleration you have to differentiate it once more with respect to time. That should give us dou to f dou x square x dot plus dou to f dou y dou x y dot. Plus dou f dou y by double dot is equal to 0. So this is something which you should verify, that if you differentiate this again with respect to time, you should get something like this. Please don't skip this exercise. What does it yield? It yields y dot y double dot given the values of x dot x double dot. Okay, so that's how the relations between velocity and acceleration components. And why are we saying the acceleration velocity components? Well, x dot is the x component of the velocity and x double dot is the x component of the acceleration. Similarly for y and z. So one of the situations which occurs very commonly in things around us is that the velocity is known uh, function, okay, and once that is known, how do we find the acceleration? It's uh, theoretically straightforward, but we'll just go through that exercise so that we don't feel lazy doing it when it has to be done in a larger or a complicated situation. Okay, so consider a case in which the velocity is a known function of the position x comma y comma z of the moving point time t. Okay, so this happens very commonly in fluid mechanics. Okay, when you have a fluid passing through, and you at any given location you know the velocity. Okay, so once that is known, then the acceleration component, how do we find that? So So let's pose the problem or the question. Given the velocity at any given location, the acceleration components of a material point with r t is equal to x I hat plus y j hat plus z k hat. Okay, so I may start using the hat symbol for I, j, k, the unit vectors, but I hope it won't really confuse you in any way. I am just too used to that. Okay, so this is a position vector x, y, and z, and obtained as the acceleration r. Ax is equal to d by dt v of x comma y comma z comma t. How do we know this? Over here, Ax is equal to Vx dot. Okay, so exactly that what we are doing over here, differentiating with respect to time. Okay, so this would mean that, let me just write it nicely over here. This would mean there's a limit of delta t tending to 0, delta of Vx by delta of t. That means there's a limit of delta t tending to 0 Vx plus delta t comma t plus delta t minus Vx So Vx of rt plus delta t comma t plus delta t minus Vx of r of t minus r of t comma t. Okay, that's how delta Vx is written. Okay, what I have done is I have combinedly written this, okay, as r. That is what has happened over here. Rather than separately writing that x of t plus delta t comma y of t plus delta t comma z of t plus delta t, I have just written it like that. Okay, so I hope this is not a problem. Okay, now this is written as dou vx by dou x dx by dt plus dou vy by dou y dy by dt plus dou vz by dou z dz by dt plus dou vx by dou t. Okay, so how has this been written? You have to just look over here, come from here to here. Okay, so you want to differentiate this velocity with respect to time. Okay, and you can write this particular term. Okay, so this is something which I can leave out for you to sort of play with. Okay, verify this particular step, how it has come. And once this is there, you can clearly write that AX is equal to 2 Vx by 2 t plus 2 Vx by 2 x into Vx. Okay, this particular term is written as Vx plus 2 Vy by 2 y Vy plus 2 Vz by 2z Vz. Okay, so we can similarly write, when I say similarly, it means you write Ay is equal to d by dt Vy, okay, x comma y comma z comma t, and then proceed ahead. Okay, this should give Ay is equal to 2 Vy by 2t plus, okay, I'm sorry, this should be, there's a misprint. There's a misprint, it seems, in your textbook. It shouldn't be like this. I'll just make this correction. I'm sorry, I should have seen it there itself. Okay. There you go. Okay. So this would make it as 2 Vy by dou x into Vx plus dou Vy by dou y into Vy plus dou Vy into dou z to, sorry, Vz. Okay, and sorry, then you have Az is equal to dou Vz by dou t plus dou Vz by dou x Vx, I'm sorry, and dou Vz by dou y Vy plus dou Vz by dou z into Vz. Okay, so this is all combinedly called as equation 113, and the symbols are important. Okay, so d by dt is a material time derivative for a specific material point. Okay, whereas dou by dou t is a time derivative at fixed spatial position. So I'll reuse different colors perhaps over here, or let me use green over here. So d by dt is a material time derivative. Okay, and this particular term, okay, dou by dou t is the time derivative at a fixed spatial location. Okay, so this partial and ordinary differentials is something which should be clear to you by now. If not, I have highlighted to you with the green and blue ink accordingly. Okay, so we'll now be moving to the kinematics of a point in cylindrical polar coordinates. Okay, coming to this discussion on kinematics of a point in cylindrical polar coordinates. So we'll need a really nice diagram to start off with. Let's show all these axes over here and we'll proceed accordingly. Let's see. So let me first draw the frame as usual. And then let me draw the x, y and z axis just because we have understood it right now. So you have z, you have y, you have x, okay, and this point is O, and we have seen that at least in the Cartesian system we have shown that the velocity and acceleration doesn't really matter on your choice of O. So O could have been O dash and nothing would have changed. Okay, so there's this point P, the material point P. Okay, so this point is, again to repeat, that it's inside a rigid body. Okay, it's one point of interest for now. This is Rp is equal to Rt. Okay, so this is what we have in the Cartesian system. Now in the polar coordinates we have r of t, we have phi of t and z of t as the coordinates of a moving point. So at any given time these are the coordinates. Let me say are coordinates of a moving point okay. So let me just draw the other system. So we have this ER, we have a E phi, they are mutually perpendicular, and clearly we have a EZ. Okay, so this goes up. Okay, so we have the ER, E phi and EZ, the unit vectors along these three directions. Clearly this is your phi, okay, and the position R is given by this vector over here, R of t, okay, and the Z of t is given by this length. Okay, let me try to use a different color. Okay, there's been a lot of damage. Let's see. This is the frame F, this was X, and okay, so let me show the, this is phi of t, this is r of t, and this is z of t. Let me just switch back. Okay, just like this one. Okay, E of phi. Okay, so the coordinates of these point is clearly x of t, um, y of t, and z of t. So if you go up over here, I should use a black ink over here. So this is z of t. The x coordinate is x of t. Okay, and we can just extend it a bit. Okay, and then on you have this as your y of t. Okay, so you have all the three coordinates. Okay, so ER, which you see over here, is the radial outward unit vector. Okay, in direction of increasing r. Okay, so as r keeps, so this is the radial direction, this blue line which is shown. Okay, and as r keeps on increasing, that's the direction of ER. Okay, and that is tangent to the radial coordinate line r for phi is equal to constant. So phi and equal to constant, and z is also equal to constant over here. Okay, similarly E phi, so this is something which you should be able to visualize. Okay, the tangent to the radial coordinate line r where phi is equal to constant, z is equal to constant. In this particular diagram you should be able to visualize this, so this is a good time to pause the video to do that. Okay, then you have the E phi, this is the transverse or circumferential unit vector again in the direction of increasing phi. Okay, so phi is the angle which is measured from the x-axis. Okay, so as this keeps on increasing, that's why you have E phi along this direction over here. Okay, and clearly it is along the circumferential coordinate line phi where r is a constant and z is a constant. Okay, so I'm not writing that again, but you should be able to visualize that. And similarly Ez is the axial unit vector in direction of increasing z. So again in this case r is equal to constant and phi is equal to constant. Similarly, here you have the r equal to constant and z equal to constant. Okay, so all of them form a triad. Okay, and so ER cross E phi EZ, okay, and E phi cross EZ ER and EZ cross ER E phi. Okay, so this is what we have. So let's try to visualize first of all some of these things. Okay, I mean, though I have left out for this for you to visualize, but let me help you out with a couple of them. ER is tangent to the radial coordinate r, okay, where phi is a constant and z is a constant. So let me come back over here. Let me draw another one. ER, okay, and it goes all the way like this. So on this line, okay, z and phi are constant, this radial line, okay. So the way you can imagine is you can have some sort of a, okay. Now similarly, let's take up the last one, which is this EZ, okay. In this one, the r and phi are constant, so this would be the direction. R and phi are constant. Okay, so if you move along this direction, the r and phi will not change. That's the idea. Similarly, if you move along this direction, okay, if you move along this radial direction, the z and phi will not be changing. It will be constant. And similarly, if you move along the circumferential or this transverse unit vector, which is phi, this line, over here r and z are constant. So they may have different value of constant, but they will not be changing. So that's the direction. This is the direction of E phi. Okay. So tangent to the circumferential coordinate line phi. Okay. So all of them are tangent to the circumferential coordinate line. Okay, so once this visualization is clear to you, we can, again, we have written about the triad over here, and let's try to write out right-handed. So we'll just follow the right hand triad. Okay, I mean, some of the people use a left hand triad, but I would suggest you to please use this for a uniformity in your understanding for this course. Okay, I myself use it all the time, so it's easy to visualize. So you use the right hand thumb rule to get all this. Okay, now the radial ER direction can be written as cos phi I hat plus sin phi j hat. Okay, how is this written? What you have to do is just let me draw. I mean, you can see this particular figure which you have, okay, and then you see the direction ER over here. Now this has to be written in terms of the x and y axis, because clearly, I mean, this, it is actually 0 of k cap, so that's why we are not even writing it. Okay, so this is how we can write. Now how do we know that we can write it cos phi? Well, there are several ways. Okay, one is that the if you take a dot product between ER, okay, and cos and I hat, you should get a cos phi. And similarly, you can take a dot product with the y direction or the j cap direction, and you will get a sine phi. Okay, so that way you can write the radial coordinate in terms of the Cartesian coordinate. Okay, similarly, you can write a e phi of t is equal to minus sine phi of I hat plus cos phi of j hat. Okay, so this can be written, and I mean, if you will be learning direction cosines sometime in the future, this will be much more easier to do with that. But for now, you can continue writing it like this. It's easy to visualize as well. Okay. Okay, so now if you want to write the time derivative of this unit vector, okay, how would you go about it? Well, you can take a time derivative with respect to f, okay, minus sine phi I hat plus cos phi j hat phi dot. Okay, because I dot and j dot will be 0. Okay, so this is your answer. Phi dot and e phi hat. Now this is a question which you should try to answer. Why is I dot and j dot equal to 0? Okay, we have already discussed this in these lectures, so you should go back and check and then come back to this, please. Okay, no need to rush ahead without knowing this. Similarly, e phi with respect to f is equal to minus cos phi I hat plus sine phi j hat phi dot. And then Ez is equal to k hat, and Ez is equal to k hat. Okay, that's obvious because the direction of Ez is the same as that of the z. Okay, so this is the same as that of k cap. So Ez dot with respect to time, or Ez dot with respect to this frame f is equal to 0. Okay, because k dot will be equal to 0. So it's not just I dot or j dot equal to 0, it's also k dot is also equal to 0. So this is equation 114, all of them. Okay, and they will be very useful in the future. Okay, so we will it will be implied that a time derivative is actually a time derivative with respect to the f frame. Okay, so in the future you will not see this with respect to f written. If it's not given, you should know it's a time derivative with respect to f frame. So we want to now find the acceleration and velocity. Okay, so the easiest way obviously is to be able to write this r, which is the position vector of a point, as what are the three coordinates? Rt of er hat t plus z of t ez of t. Okay, now you may wonder why we are not writing, say, phi of t and e phi of t. Okay, the reason this is not written is because the dependence of r on phi is implicit through dependence of er and ez on phi. Sorry, yeah, er e phi on. Okay, that's why we don't separately write it. You can check the expressions of er and e phi. Okay, so we don't separately write it like that. So er and e phi are both dependent, so we just write the black part over here. Now with this as the position vector, you want to write the velocity, that will be equal to r dot, that will be equal to we'll use the chain rule over here. So we'll write r dot er hat plus r er hat dot plus z dot ez hat plus z ez hat. Okay, so this is what we get as our velocity. Now this particular term can be written as r dot er hat, okay, plus, let me just write this part first. Okay, now try looking at r plus z dot. Okay, try looking at this term and this term. we want to say that you have a r phi dot e phi. Okay, so can you think of a reason why? Basically this blue part, this, sorry, so the summation of this plus this is equal to this. Okay, let's try to see if we can actually do that. So we have r into er dot, that is phi, we're using this over here, phi dot e phi hat plus z into ez hat. So this is 0, okay, and hence this term is equal to this term. So that's how we have written this. Okay, just rub this out. Okay, so we should be able to say that this is equation what, 115. Now coming to the acceleration of the material point of this rigid body, so we want to take a time derivative of this v. We'll apply the chain rule and we should have r double dot er plus r dot er, sorry, I should just write it like this, plus r dot phi dot plus r phi double dot e phi plus r phi dot e phi dot plus z double dot ez plus z dot ez. Okay, so this should come after the chain rule and you should be easily able to verify this. Now you have to use the simplifications above, I mean this one and this one. Okay, and then we should be able to write the acceleration just like we have done for the velocity as r double dot minus r phi dot whole square er plus 2r dot phi dot plus r phi double dot e phi z double dot ez hat. So this is 116 and you should be able to verify this. Okay, just like we have done the derivation for velocity, you should be able to do it for the acceleration in the cylindrical polar system. Now with these expressions for velocity and acceleration, we want to separate the radial and the transverse and the axial parts. Okay, So VR is what? R dot. Okay. V phi is equal to R phi dot, and Vz is equal to Z dot. The magnitude of this V is Vr square plus V phi square plus Vz square whole square root. So that would be R dot whole square plus R square phi dot square plus Z dot square. Okay. This is equation 1.17, and similar to this you can write for the acceleration. The radial part would be R double dot minus R phi dot square. A phi would be 2R dot phi dot plus R phi double dot. Okay, I should not here use this. Plus, and then the AZ should be Z double dot. Okay, and the magnitude of A would be AR whole square plus A phi whole square plus AZ whole square. This is equation 1.18. So we are just being lazy over here, not writing the terms actual in this, but I hope you can easily write it. So I hope it is easily seeable that despite you not explicitly taking the dependence of R on phi, the velocity and accelerations will have all these terms, okay, with lots of phi's around. So you were right in doing that. Okay, there was no problem doing that. Okay. Okay, now let's say that if your A phi is some sort of notes which you can take from this is that you have A phi is equal to what, 2R dot phi dot plus R phi double dot, or you can write it as 1 by R d by dt of R square phi dot. Okay, so this is the same as this. Okay, so you can expand this and see that you will get exactly that. Okay, this is equal to 1 by R d by dt. Now if you look at R square phi dot, okay, you can write it as R into R phi dot. Okay, and this will be 1 by R d by dt. R into R phi dot is V phi. Okay, this is equal to V phi. So you can see from over here. So A phi is equal to 1 by R d by dt of R of V phi. Okay, so this shows that there is some sort of a relationship, but it's not as straightforward as taking just a time derivative of one component. Now AR, which you see over here, and VR, which you see, okay, both here and here, can you just say that AR is a further time derivative of VR? You cannot. Okay, just look at these two expressions. By differentiating this with respect to time, you will not get this. and similarly a phi is not equal to Vr dot, right? If it is a phi, okay, it is not equal to Vr dot clearly, and a phi is also not equal to V phi dot. You've just seen that over here. The whole point, the whole reason why this is not happening, okay, is because Er and E phi are not, not constant in F. Not constant vectors. Unlike the I hat, J hat and K hat, which were constant vectors in F. Okay, so that's why remember I hat dot and J hat dot and K hat dot was equal to 0. This is not the case over here. Clearly you can see that ER dot and E phi dot are all having some values. Well, EZ dot is an outlier, okay, but other than that the other two components, other two coordinates of this system are not 0. Okay. Now let me come back. We call this point as M. So phi dot is termed as the angular speed of the projected line OM. Why is this a projected line? Because, so first of all, it's a OM is a projection of OP, right? So if you project this OP on this ER in this ER direction, you will be getting OM. Okay, so OM is the so phi dot is the angular speed of the projected line OM about the z-axis. Let me make that note over here. It's easy to visualize it over here. Thankfully we have space. So phi dot angular speed of the projected line OM about z-axis. Every time you define an angular speed, it is about something, okay, about a point, about a line, whatever, and its angular velocity is phi dot k hat and angular acceleration is phi double dot k hat. Double dot. Okay, so these are some other definitions of angular speed, angular velocity and angular acceleration. Now this is again, as I have been very specific, angular speed of the projected line OM. A moving point will not have any angular velocity ever. Okay, like P does not have an angular velocity because it has no orientation as such. So let me make that as a separate note. So you should be careful in discussing the concepts of angular speed and velocity. It's of the projected line. A moving point has no angular velocity as it has no orientation. Okay, so you should be able to think about this statement. Why is the orientation needed at all? Okay, you have to convince yourself of the statements. If not at first, at some point in the near future, you should be able to understand this. Okay, so just like the AR and VR are not like, so the AR is not equal to VR dot, okay, and A phi is not equal to V phi dot, I'm sorry, I should write this, okay. Similarly, if you integrate AR and A phi, you will not get VR and V phi. The integrals of AR with respect to time do not yield VR V phi, but integral of R A phi yields zero to t hold on, okay, so you have integral of R A phi dt, okay, 0 to t. So R A phi is you have to use this expression, okay. R A phi, R will go up over here, okay, so this will be equal to R d by dt of R V phi dt, and this is R of t V phi of t minus R of 0 V phi of 0, okay. So it's a definite integration, okay. So this is what we get. So this is equation 1.19. So the integration of AR and A phi will not give you VR and V phi, but luckily the integration of R A phi is giving us R V phi. Okay, so that's something which is very important to note, and it will be useful at some point when we start solving problems. Okay, so these tricks help over there, knowing this. Okay. So if you have, say, a planar motion, we have already known what a planar motion is. In a plane z is equal to constant. Then we can say the axial components okay, so the axial, let me just come back. Vz and Az are 0. Okay, obviously there's no motion in this one, and hence there's no velocity and acceleration in the axial direction. So the velocity will just be, what you do is just go over here. Okay, you have already derived an expression for velocity, this one. Okay, just skip the Ez hat part. Same for acceleration as well. So for a planar motion, we'll be able to write that the velocity is equal to r dot er hat plus r phi dot e phi hat, and then the acceleration is equal to r double dot minus r phi dot square er hat plus 2r dot phi dot plus r phi dot e phi. And just like the other case, we will not reuse the Ez component because it's a planar motion. Okay, and there is a physical reason for it. It's not just that you see z everywhere and remove. Okay, the logic is that since there is no motion in the z direction, hence there cannot be a velocity or acceleration, and hence it's easy to just ignore the other parts. Now if you look over here in this diagram, there are certain other expressions which we can write. For example, can we write the radial component squared? R square is equal to x square plus y square. Okay, and x can be written as r cos phi and y can be written as r sin phi, and then this angle phi can be written as tan inverse of y of x. So those are some two-dimensional things which were very easy for us to write. So we can write the relations between Cartesian and cylindrical coordinates r is equal to x square plus y square, phi is equal to tan inverse y by x is equal to r cos phi, and y is equal to r sin phi. Okay, so 1.21 is what we have. We'll just be invoking it many a times. There may be certain situations in which some part of the analysis has to be done in the Cartesian system and the other part is more convenient to do in the cylindrical system, and hence we should be knowing the relationship between the two. Okay, so the cylindrical coordinate systems are really very important when you have, say, a situation like let's use an example of a turbine. So I'm referring to something called a Pelton turbine. Of course, the others will also have their own analysis. At least the cylindrical coordinate part is common. So what it has is that it has these blades. Okay, and then there is sort of water coming on from a big height. Okay, there's a lot of height, and then there's a water is stored over here and water flows down, and so this potential energy stored over here gets converted to the kinetic energy, and because of this the water will hit these blades in this directions, and then there will be a rotation of this turbine. So because of this rotation you can generate electricity. Okay, so just like the fan, you supply electricity and then it rotates, the other is possible also. I mean, if you are somehow able to mechanically rotate, you can generate electricity. You must be aware of these principles of electromagnetism. So this can be used in uh, uh, turbines. Now, if you focus on one material point, say like this, and this is your origin, let me just, this is say your point of interest. You can define this in terms of ER and E phi and EZ, okay, and in planar of course you can just ignore the Z part, and clearly if this coordinate system is attached to it, it will be a function of time and it will change, right, because it's a rotating system, like the turbine will be rotating, and hence you can proceed ahead with this. So the ones among you who are lucky enough to be learning say fluid machinery courses, perhaps mechanical engineering is definitely one discipline where it happens. We have to they'll be using this concepts over there. Perhaps they'll also be doing experiments over this. So that's one example where this is needed, and in my experience of having worked in at least solid mechanics, I find the polar coordinate system much more useful because most of the applications of engineering are actually easily doable in this coordinate system. There are very few examples of very few situations where the Cartesian system is used. We must know both definitely, but please don't ignore this. Okay, the whole point of all this is so that you don't ignore this system. Okay, now if the, just like the previous analysis of a Cartesian system, the last part of that analysis was that we were using a implicit trajectory, okay. Similar we want to do it over here. The path will be now used as a parameter which is not time. So let's see if the path if the path is prescribed not as a parametric equation in time. Remember we had done this for the surfaces G of xyz is equal to 0 and H of xyz equal to 0. They were not explicitly containing time, okay. We are doing exactly similar thing over here, okay. In this case we will say that the coordinates R are actually f of phi and z is equal to g of phi. So then the relationships between the time derivatives of r, phi and z can be obtained just by differentiating it with respect to time. So r dot will be equal to df by d phi into phi dot, okay. Similarly z dot is equal to dg by d phi into phi dot. R double dot is equal to d2f d phi square phi dot square plus df d phi phi double dot. And similarly you can have the, let me just write it here, yeah, this space, z double dot is equal to d2g d phi square phi dot whole square plus dg d phi phi double dot. Let's call this as equation A. So this is just the chain rule of differentiation, okay? If the values of one out of this r dot, phi dot and z dot and one out of r double dot, phi double dot and z double dot are known, then you can solve the remaining four values, okay? So if phi dot is known as say phi dot is equal to h of r phi z t, okay, then using this equation, r dot and z dot are obtained first, okay. So phi dot is something which is already given, so you will just substitute it over there and then you will just find r double dot and z double dot, okay. For this you will have everything else other than phi double dot, okay, and that is something which you can just find out. Phi double dot will be equal to d by dt of h of r phi z t, okay, and that would be equal to dou h by dou r dot plus dou h by dou phi dot plus dou h by dou z dot plus dou h by dou t. Okay, this is something which is similar to what we had seen in for the Cartesian system. Now there is another definition. A dot is defined as jerk, okay. The time derivative of the acceleration, a dot, is defined as a jerk, and it's normally associated with, say if you are moving in a car and suddenly the acceleration drops, so that change of the acceleration with time, if it's not very small, then the passengers will feel discomfort, okay, and that's where this is important. So one example where you can use this is that is the discomfort experienced by passengers of a vehicle which is accelerating or deaccelerating very fast, okay, extreme situations, that's where that is felt. So it has its own meanings, especially in vehicle crash and impact, and how the impacts of vehicles affects its passengers, okay. So some of the other comments which one can make are that the choice of the origin and the orientation of the coordinate axis in reference frame is not unique. We have seen that enough number of times, right? Take O or O dash, displacement doesn't change, the velocity doesn't change, and so on. So since the origin or O is not really unique, okay, we can choose it to make our problems or our situations easier. Hence you will always have that question in mind, that where should I change my origin, how should I take the orientation of my coordinate axis, and things like that, and many of it comes by experience. Okay, so the more situations or problems you try to see or visualize, the more experience you get in your uh, wisdom of choosing the origin and the orientation of this polar coordinate axis. Okay, so that's where we can discuss this polar coordinate Cartesian systems, and as I've said, it will be very useful